Most people never walk past valuable gemstones because they're hidden. They walk past them because they don't recognize the evidence: a thin band of iron staining, a quartz-filled fracture, an unusual crystal shape, a subtle change in rock texture. To most people, these details mean nothing. To an experienced field geologist, they can mean everything. Because professional prospectors rarely search for gemstones, they search for geological clues. And sometimes those clues lead to gemstones worth a few dollars per carat. Or in extraordinarily rare cases, specimens valued in the millions. But geology teaches an important lesson. Most discoveries are modest. Color, clarity, rarity, size, and geological setting determine value. The real skill isn't finding gemstones, it's learning how to read the earth itself. Before any investigation begins, experienced prospectors typically carry a geological hammer, a 10x hand lens, hardness picks, an unglazed porcelain streak plate, a field magnet, sample bags, a field notebook, a topographic map or GPS. Because every geological investigation begins with observation. Number 10. Garnet. At first glance, there's nothing remarkable about this outcrop. Dark minerals, layered rock, thin quartz bands. But these are exactly the environments experienced prospectors investigate. Notice the foliation. Notice the mica content. Notice the mineral layering. These are metamorphic rocks. And metamorphic environments often produce garnet. The weathered surface disappears. And suddenly the geology tells a different story. A crystal, deep red, protected inside the rock. Most garnets found in the field have modest value, but certain varieties, including green demantoid, vivid savorite, and fine hessonite, are among the most sought-after garnets in the world. The important lesson isn't the price, it's the geology. How do prospectors identify garnet? Start with crystal habit. Most garnets display rounded crystal forms and lack cleavage. Next, test hardness. Most garnets scratch glass easily. Then perform a streak test. Notice the result. Little to no visible streak, and that's important. Streak color is often more reliable than surface color for mineral identification. Unlike iron oxides, which often leave red-brown streaks, garnet typically leaves none. No magnetic response. Most garnets are non-magnetic, unlike magnetite and certain other iron-rich minerals. This helps prospectors eliminate several common lookalikes. Under magnification, garnet crystal faces usually appear smooth rather than striated. What should a prospector do next? Map the metamorphic zone. Follow the host rock. Search for additional mineral associations. Because geological systems matter more than individual specimens. Number 9. Spinel. Some of history's most famous rubies were eventually discovered to be spinels, and that mistake tells us something important. Color can be deceptive, geology usually isn't. Notice the host rock, coarse marble, dark alteration minerals, structural contacts. These are exactly the environments where spinel forms. Now examine the crystal itself. Notice the shape. Many spinels form octahedral crystals. Garnets usually do not. How do prospectors identify spinel? Use a hand lens. Study crystal habit. Test hardness. Spinel typically measures around 8 on the Mohs scale, and unlike many red minerals, it lacks obvious cleavage. Again, the streak remains white. Another important clue: fine spinels are increasingly prized by collectors. Exceptional spinels, particularly vivid red and cobalt blue varieties, can exceed $10,000 per carat. Spinel also occurs in a remarkable range of colors: red, pink, blue, purple, orange, and black. But spinel matters for another reason. Spinel and corundum often occur in similar geological environments. Finding one may justify searching for the other. What should a prospector do next? Trace the marble. Map the contacts, investigate alteration zones, because geological clues often travel together. Number 8. Ruby. Few gemstones capture attention like ruby, but experienced geologists know something beginners often don't. You don't search for rubies, you search for ruby geology. Notice the surrounding minerals, notice the deformation, notice the alteration patterns. These clues matter more than color. Rubies often form in aluminum-rich metamorphic environments. Marble, gneiss, amphibolite, structural contact zones. These are the places professionals investigate. Notice the fracture density, notice the oxidation, notice the alteration halos. No single clue proves ruby, but together they build evidence. How do prospectors test ruby? Begin with hardness. Corundum ranks 9 on the Mohs scale. Steel won't scratch it. Quartz won't scratch it. Notice the result. No colored streak. Another clue supporting corundum. Then examine crystal habit. Because many natural rubies appear dull, fractured, and surprisingly ordinary, which is exactly why people walk past them. One more important lesson. In ruby, color saturation and transparency often determine value more than size. Clarity also matters. Interestingly, certain rutile silk inclusions can help gemologists confirm a natural origin. Among collectors, the most prized rubies display the legendary pigeon's blood color, a vivid saturated red with exceptional transparency. What should a prospector do next? Follow the alteration, map the structures, investigate associated minerals. Because gemstones rarely occur in isolation. Number 7. Tourmaline. If experienced prospectors suddenly stop walking, there's a good chance they've found pegmatite. Because pegmatites produce some of the most remarkable crystals on Earth, including tourmaline. Notice the crystal shape: long, prismatic, strongly striated. These grooves are one of tourmaline's most reliable field indicators. Pegmatites form during the final stages of magma crystallization. As magma cools, rare elements become concentrated: lithium, boron, beryllium. These elements allow unusual crystal structures, colors, and chemistries to develop, and under the right conditions, gemstones form. Tourmaline itself occurs in one of the widest color ranges of any gemstone: green, pink, blue, black, and even the famous watermelon varieties. Among collectors, the neon blue Paraíba tourmalines rank among the most valuable tourmalines ever discovered. How do prospectors identify tourmaline? Use a hand lens. Look for longitudinal striations. Inspect pegmatite pockets. Search fractures and cavities. What should a prospector do next? Trace the pegmatite. Map its orientation. Investigate structural breaks. Because the best crystals often occur in isolated pockets hidden deep inside the rock. Number 6. The red crystal that shouldn't be here. A geological mystery. At first glance, this rock appears completely ordinary. No crystal faces, no bright colors, no obvious indication of value, just another weathered cobble. But notice the fractures. Notice the iron staining. Notice how the oxidation follows specific pathways. Not random. Localized. To a field geologist, that means something happened here. Weathering hides information. Fresh surfaces reveal it. And suddenly the investigation changes. A crystal, deep red, embedded inside the rock. The explanation appears obvious. Garnet, case closed. Then he stops. Wait, that's unusual. The crystal faces appear faintly striated. Garnets don't typically display this feature. And the color isn't uniform. Subtle internal zoning becomes visible, almost as though the crystal recorded multiple stages of growth. Then another detail emerges. A faint star-like internal pattern. Even covered in dust, there appears to be a subtle internal glow. Not reflected light, something deeper. Not enough to identify the mineral. but enough to challenge the original conclusion. For several seconds, he says nothing, because every experienced geologist recognizes this moment. It's the moment when the evidence no longer supports the explanation. And when that happens, the investigation begins again. The crystal scratches quartz. Its streak remains colorless. The field magnet produces no response. But none of these observations eliminate every possibility. Could it still be garnet? Perhaps. Could it be spinel? Possibly. Could it be corundum? The geology allows it. Or are we looking at an entirely different gemstone-forming system? The next step isn't guessing, it's investigation. Follow the fractures, map the structures, trace the mineralization, search for alteration zones, because geology rewards evidence. And then one final clue appears. Dark mineral bands, parallel to the fracture system, not random, not superficial, and possibly formed during the same geological event that created the red crystal. If that's true, then our original interpretation may be completely wrong, and whatever happened here may be far more unusual than anyone initially suspected. Number 5. Aquamarine. Most gemstone hunters search for color. Experienced prospectors search for pegmatites. Notice the giant feldspar crystals. Notice the massive quartz. Notice the pockets and cavities. These features tell a geological story. Pegmatites represent the final stages of magma crystallization. As magma cools, rare elements become concentrated, and when the chemistry is right, those elements can produce gemstones, including aquamarine. Dust falls away. A pale blue crystal appears. Not brilliant, not dramatic, just subtle, which is precisely why many aquamarines remain undiscovered. Aquamarine's color comes from trace amounts of iron, and unlike the vivid gemstones often shown in jewelry stores, natural aquamarine frequently appears pale when first discovered. Some specimens are heat-treated after mining to deepen their blue color. The most valuable aquamarines display rich, saturated blue hues. How do prospectors identify aquamarine? Start with the host rock. Aquamarine belongs to the mineral beryl, and beryl commonly forms inside granitic pegmatites. Notice the hexagonal crystal shape. This is one of beryl's defining characteristics. Next, test hardness. Beryl measures between 7.5 and 8 on the Mohs scale. Hard enough to scratch glass easily. Unlike many blue minerals, it lacks obvious cleavage. What should a prospector do next? Follow the pegmatite. Map the pocket zones. Search for associated minerals. Tourmaline, muscovite, feldspar. Because gemstone deposits rarely occur in isolation. Number 4. Opal. Some gemstones don't form deep underground. They form close to Earth's surface, and few gemstones demonstrate this better than opal. Notice the iron staining. Notice the silica-rich weathering crust. Notice the fracture patterns. These aren't proof, but they are evidence, and in geology, evidence is where everything begins. Suddenly, the rock changes: red, green, blue, orange, not paint, not reflection. An optical phenomenon. How do prospectors identify opal? Begin with the geology. Look for silica-rich sedimentary environments. Inspect weathered fractures. Search areas influenced by ancient groundwater circulation. Some hydrophane opals absorb water and temporarily change appearance. Not all opals do this, but when present, it provides another useful clue. The famous play of color effect occurs because light diffracts through microscopic silica spheres. The more organized these spheres become, the more spectacular the colors appear. This is what separates precious opal from common opal. Among collectors, black opal, particularly from Australia's Lightning Ridge deposits, is considered among the most valuable opals ever discovered. Opal also contains water. Rapid drying can sometimes cause precious opal to crack, making proper handling extremely important. What should a prospector do next? Trace the sedimentary horizon, map the silica-bearing layers, follow evidence of ancient groundwater movement, because opal deposits often extend far beyond the first discovery. Number 3. Jade. Few gemstones are more misunderstood than jade. Many people assume they would recognize it instantly, most wouldn't. No crystal faces, no sparkle, no obvious transparency, just a heavy, weathered rock. Exactly why jade remains overlooked. The fresh surface reveals something different, a tightly interwoven texture, dense, fibrous, exceptionally tough. How do prospectors identify jade? First, examine the geology. Many jade deposits occur in metamorphic environments associated with ultramafic rocks and serpentinite. Jadeite, the rarer of the two primary jade varieties, forms under extreme pressure conditions associated with subduction zones. The finest emerald green imperial jade specimens can rival the value of top-quality emeralds. Second, test toughness. Jade resists breaking far better than many similar minerals. Notice the fibrous texture. Notice the waxy luster. These are important clues. What should a prospector do next? Map nearby serpentinite bodies. Investigate fault zones. Search stream gravels downstream, because erosion often transports jade far from its original source. Number 2. Alexandrite. Some gemstones are valuable because they're beautiful. Others are valuable because they're rare. Alexandrite is both. At first glance, this crystal appears green, but appearances can be deceptive. Alexandrite was first discovered in Russia's Ural Mountains during the 19th century. Even today, it remains one of the rarest gemstone varieties ever discovered. Exceptional specimens can exceed $50,000 per carat, making them among the most valuable colored gemstones on Earth. Then something remarkable happens. The crystal changes color. Green becomes red. Not because the crystal changed, because the light changed. How do prospectors identify alexandrite? Begin with the geology. Alexandrite requires an extremely unusual combination of elements: beryllium, chromium, and very specific geological conditions. Its remarkable color change occurs because chromium atoms absorb different wavelengths of light. Under daylight, green dominates. Under incandescent light, red emerges. Few minerals demonstrate chemistry more dramatically. Alexandrite ranks 8.5 on the Mohs scale. Hard enough to survive weathering and transport. What should a prospector do next? Map pegmatitic contacts. Investigate chromium-bearing alteration zones. Search metamorphic host rocks, because rare chemistry often creates rare gemstones. Number 1. The red crystal revisited. The red crystal remained unexplained. So the investigation moved upstream. Notice the fracture orientation. Notice the alteration. Notice the dark mineral bands. These features aren't random, they're structural. And structures control fluid movement. Fluid movement creates mineral deposits, which means geological structures create opportunities. Another crystal appears, then another, and another. The same internal zoning, the same faint striations, the same colorless streak, the same unusual optical behavior. At first, garnet still seemed possible. Then another observation changes everything. The crystal scratches topaz. That shouldn't happen, because only a small number of gemstones approach this level of hardness, and one of them ranks among the hardest minerals on Earth. Then the crystal reveals one final clue, a 6-rayed optical effect, subtle but unmistakable. This optical phenomenon develops only under very specific crystallographic conditions, making it one of the most important observations yet. For several moments, nobody speaks, because every geologist recognizes this feeling. The moment when the evidence stops supporting the original hypothesis and forces a new investigation. Could this be a rare form of corundum? Suddenly, the geology allows it. If that's true, then these structures didn't simply transport mineralizing fluids, they created an entire gemstone-forming system. And if that interpretation is correct, this discovery could be regionally significant. If confirmed as corundum, this deposit could alter future exploration priorities throughout the region. But geology never rewards assumptions, only evidence, which means the investigation isn't over. In many ways, it's only beginning. If you enjoy geology, prospecting, mineral identification, and learning how professionals interpret the hidden clues beneath our feet, subscribe and continue exploring with us. Because every rock tells a story. And sometimes, the most valuable stories are the ones everyone else walks right past.